Cool. Hi, everyone, and welcome to our session on two-phase immersion cooling. In this session, we are going to have a discussion on our lessons and experiences from doing world's first two-phase immersion cooling deployment in a hyperscale cloud. So let me start with a brief round of introduction. So my name is Ashish Raniwala, and I'm an architect in Azure, Microsoft. And I'm joined by Hassam Alisa, Jonas Manisakis, and Mark Shaw, all from Microsoft, and we all work on different aspects of our immersion cooling program. We have Phil Tuma from 3M, who is an application specialist in fluorinated heat transfer fluids. And we have Simon Chen, who is a thermal mechanical engineer at Vivint. So before we start, let's see how immersion is connected to sustainability. So Microsoft has made a pledge to not only go carbon negative by the end of this decade, but also to remove all its prior carbon footprint since 1975 by the middle of the century. Now, this is an ambitious goal, and it requires a lot of technical innovations, both to cut down the emissions in future, as well as get rid of prior emissions which have been done already. And immersion cooling is one such technology. What immersion can do is it can allow us to first cut down the greenhouse gas emissions, secondly, reduce energy consumption, third, it allows us to eliminate the blue water consumption in the data center, and finally, it allows us to reduce our data center footprint. So all in all, actually, immersion allows us to both improve the performance and efficiency of our data centers while simultaneously cutting down the environmental footprint of the data centers, which is a win-win situation. So now, immersion and in general, liquid cooling is not just desirable, but it is also becoming essential. So as you know, the slowdown of Moore's law has increased to dramatic increases in the chip power consumption. And air cooling these chips, especially in a public cloud hyperscale data center, is becoming less and less economical. And what immersion and in general liquid cooling allow us to do is to actually make these things far denser, which would become much more sparse if we were to continue down the air cooling path. And that's why Microsoft decided to take this two-phase immersion cooling, which was deployed only in the niche of Bitcoin mining industry, and take it, and earlier this year became the first public cloud to deploy it to cool its servers in the data center. Now, we already spoke about some of the benefits of immersion cooling around sustainability. There are many other benefits of that. So one is around TCO. So you can actually so immersion can help us cut down our TCO of the data center. How so? So one is it allows us to reduce the energy consumption because we can get rid of a lot of data center level cooling infrastructure. You don't need to run the fans, for example. Secondly, it allows us to actually improve the reliability of the components, assuming we do it right, and actually cut down the cost of replacing the hardware all the time. And most importantly, it allows us to unlock all the innovation that which had been hampered by our inability to cool by making our chip, the server, and the data center all much denser. So let's make this all concrete. So let's start with Simon. Why don't you tell us about what an immersion cooling tank looks like?
All right. Hey, thank you for having me. I believe a lot of you have already stopping by the Vivint booth, and through the HoloLens 2, you can virtually see the whole tank. It's a 4-rack tank, and you can take a look at the slide. You know the spec and all the features the tank provided. And if you haven't stopped by the booth, then you still got a chance after the meeting. And so there are two most important features I think we should consider. The first is safety, right? And the second is serviceability. And our engineers working with Microsoft and 3M, we consider this seriously. So even with like my height, I'm standard to a shorter height. I can still reach to the servers inside the tank and bring it out and do all of the servicing tasks, without any challenges. So, other than that, so the safeties. So we have anti-pinch functions built in with the tank, and also pressure relief valve, so that if any shutdown scenarios or any emergent cases happen, we can have a solution to mitigate the issues.
Hey, thank you, Simon.
Thank you.
So we'll actually switch the order a little bit, because let's see. So Mark, what does it take to take a server and immerse it in this tank?
Well, one of the things we really like about Immersion is that it's easy to use. It's easy to build a system around it. You saw earlier, the previous presentation, someone had just repackaged the systems into an Immersion. What we did was we said, let's take a Project Olympus server, something that's in production, just put it in the tank, see if it works, right? And so all we had to do was some firmware modifications. I don't see any fans in there. We had to pull the fans out. We had to tell the firmware, no fans. We also had to make some changes for, the inlet temperatures and things like that, for a little bit different than with air. And so that was the easy part. So it made it really, really straightforward to deploy this into the data center. It looks just like any other Project Olympus cluster in our data center. And but working with WeWin, we really needed to repackage this to make it easy, as Simon mentioned, for lifting it out. So instead of the very deep tray that we have in an air-cooled chassis, we broke it into two pieces: the power supply piece and the server piece, so that the servers get pulled out far more frequently than a power supply. So those two parts there. You can see on the screen, the ease of deploying this. There's just a little boiling enhancement coating in place of the heat sinks in there, and it's worked out quite well. That from all of the Azure software viewpoint, they can't tell the difference.
That's awesome. So right off the bat, you're getting kind of a denser design, even without much modification. Right.
Yeah. This is denser with just using straightforward air-cooled motherboards. But of course, the fluid is capable of cooling a lot more. And so if we redesign the motherboard to be more optimized, we can actually start taking advantage of the fluid and the thermal capacity that it has.
Cool, that's awesome. All right, so let's say, we have the tank and we have the servers immersed in it. So how do you deploy these servers into the data center, and how do you operate them?
Yeah, that's a great question, Ashish. And I think even before digging into the integration of the tank to the data center, liquid cooling technologies in general and specific to Immersion kind of create a little bit of a blur on demarcation on what is data center, what is server, and what's in between. And this could also extend to what's considered facility, like the tank, for example, or the servers, and could even extend to supply chain implications. So switching to or bringing Immersion into, say, air-cooled or a cloud-native hyperscale data center does have a bunch of new elements to it compared to what we do today. So starting from tank positioning, for example, so when we're doing air cooling as of today, we have the hot aisle, cold aisle configuration, hot aisle, cold aisle containment, et cetera, all the stuff that's around airflow management. Now, we don't have to think about that anymore. Rather, bring the tank as close as possible to your physical power or cooling connections. And then we get, for example, to tank inspection and checkpoints. So we have the classical UL certification, but then we can expand to hotspots that are more related to Immersion, such as tank leaks, for example, at the initial startup. Telemetry is another important element. So if we're talking air cooling, we're talking about fans RPM. Maybe we're talking about air pressure differential in hot aisles and cold aisles. And then we're talking Immersion. We're talking about fluid temperature if we're talking two-phase heat transfer, it should be uniform saturation temperature. We're talking about fluid level, pressure. Then we have condenser side, so that or primary loop flow and temperature. So the set of telemetries are new or unique, and we had to also make sure we're getting these readings. And then we get to the actual physical connections. So the tank will have to connect to facility water, typically connects to your dry cooler, where you have the closed loop of warm coolant. This enables us to go waterless or dry cooling, basically. That's essential. And then from a power architecture, we really have options. And it's hardware dependent. So we could, what we're showing here is an Olympus PMDU native power connections. But you have all sort of options depending on the hard density, et cetera. So there is also the water loop inspection, making sure that pressure and leakage, all that stuff is sorted out. And then we get to the part where we want to fill the tank with the dielectric fluid. Now, we're starting from the assumption that we have tanks fully integrated with servers, and then we go to the priming these tanks with fluid, taking into account what's the appropriate fluid level, et cetera. And then now we have a system. We have an overall system check of the server, the tank, operation, data center, and the workload. And if all that checks, then we're in a good position.
Got it. That's awesome. So now that we have it deployed in the data center, let's talk about operations.
Yes, so that's another important step when we want to bring Immersion to scale. Creating the SOPs, the appropriate sequence of operation, to put this in the data center and have our data center operators be comfortable with how to run the tanks and service the servers. So, and these different really nice clips. So if we start to the left, you see the value of having a quick disconnect, tank level dripless quick disconnect that actually has the tank interface with the facility water. It makes deployment and decommissioning rather easy and seamless. And then moving to the tank lid, I think Simon highlighted that point. So we could go with more simple manual tank lids that either could be an uplift or a slide. Or we could go fancier, and what we're showing here is an automated lid. When we have automated lid, we also have to think about safety. We could be using laser curtains to ensure we don't have any safety issues with the operator. Now, servicing the server itself, let's start with blind mate really helps for power. If we have blind mate power at the bottom of the tank, really makes servicing these servers easier. Loosen a thumb screw on the server, remove cable, pull the server upward, and basically we have we can take the server out, and we have some settle time. Here, we're talking about two-phase fluids with lower surface tension capability. So we're basically saying in a couple of seconds, we have a dry server, put it on a table, and do whatever surface, and then engage the server back in. And overall, to the picture to the most right, cable management is always important, obviously, and we bring all the cabling to the upper side of these servers.
Cool. Thank you, Sam. So I think you mentioned the fluid a few times, so let's talk about fluid a bit. So Phil, you're the expert here. So what are the big challenges, or rather what's one single big challenge that you see when it comes to the fluid?
Yeah, thank you, Ashish. As you mentioned, there have been some big crypto deployments, right? This is one of the first rack scale deployments with conventional IT. And one of the things we've learned is that there can be a lot of contamination in the hardware. What kind of contamination? Well, there are hydrocarbon oils, a lot of them, aliphatics, phthalate esters, things like that, some of them plasticizers, that can become extracted into the fluid. And most of these things aren't very soluble in the fluid, only a couple hundred parts per million, but in a two-phase application, they can become deposited by distillation on the boiling surfaces. And as I'll show you on the next slide, that can affect performance pretty dramatically, really. Oops, so sorry. When you actually, am I still on?
You're still on, so don't worry.
When you actually look at this table, and this is a pretty inclusive list of the contamination sources, you find that a lot of them are really unnecessary in an immersion environment and could be eliminated outright. There are clean alternatives for others. A classic example is a PVC clad cable, right? PVC is clad with an extractable oil, diactyl phthalate, and some low smoke zero halogen cables are 95% cleaner than PVC. So that's an easy fix. And you do these things, it's relatively easy to drop the contamination burden from something on the order of a kilo, which is what we observed in this project, to something that's much easier to manage with the filtration system, which is, as the slide says, based on activated carbon. The fluid is flowed through an adsorbent, and concentrations can be driven very, very low.
All right.
And here are some actual data from the project, which I find fascinating. We take the fluid periodically and we analyze it by gas chromatography, and we can calculate the total hydrocarbon concentration, quantified here in parts per million. You'll see the junction temperatures on the processors follow the contamination level pretty closely. And so what we observed at points where the concentrations were high, you could see oil on the boiling surfaces in some cases, and the junction temperatures are impacted by that. But this process is completely reversible. Once the filters were changed with sufficient frequency, the contamination burden came down and the junction temperatures returned to normal.
Got it. So we have the ability to react if something goes wrong.
Exactly.
That's pretty cool. All right. So we started the conversation with talking about sustainability and performance improvement at the same time. So Jonas, do you want to elaborate on that?
Yeah. So initially we started thinking about, okay, we have this relatively high cooling capability with two-phase immersion cooling. We have cold plates, on the horizon. We have pretty advanced air cooling with remote heat sinks. So we're thinking about how we can make more performance out of the same platform. And it's quite nice because we have the capability to kind of integrate the software platform on Azure, which we manage, and get kind of information from the hardware. We can do this co-design and co-optimization in order to kind of understand how much more thermal headroom we have, how much more power we have at the data center level. And thus, maybe provide more performance to our VMs. So we actually wrote a couple of research papers. The first one is, I think, it should be over there. I don't even see what's.
Yeah, I see two of them there, right?
The one, talks about what is the opportunity for all different cooling technologies. So air at different conditions, cold plates, and then two-phase immersion cooling. I think one phase is actually missing from that. And the second actually talks about how do you design, kind of as a cloud provider, a software platform that sits in the middle of the hardware and the VMs, kind of is the arbitration of all the available budgets that you have and the available underutilization that you have at different levels of the hardware hierarchy, basically. And then understands all the customers on top and tries kind of to do the arbitration and say, look, these customers are important, these are internal and they're lesser important, or these customers, they need performance at this particular point in time. So, assuming that you have cooling and power budgets and the other budgets that we have in the data center, we can redirect more performance and fix particular issues that we see during operation.
I see. So you're providing the extra compute where it's actually going to help, not just.
Yeah. And two-phase immersion cooling is nice because, as we're going to see in the next slide, which is quite complicated, the two-phase immersion cooling is actually probably the best cooling technology that we have at the platform level. And maybe you can do local optimizations at the CPU level or the ASIC level, and say maybe two-phase cold plates are they have spectacular local performance, but at the platform level, memory DDR5, DDR6, the power is going up. Storage, flash, the power goes up. So at the platform level, this is the best thing that you can do because you have basically, I wouldn't say unlimited cooling, but very high levels of cooling available. And now you can think about this, leveraging this at different components, and the system understands all these different capabilities and tries and goes and maybe boosts memory. There's cooling budget. There's no implication into phase immersion cooling, right? And this actually goes very well with our platform management. So if you think about how you can make the cloud platform a little bit more sustainable, what is the best thing that you can do? Well, actually, although this overclocking, like we call it, it sounds counterintuitive because the power performance trade-offs are pretty terrible at the high end of the spectrum. Like if you want to make a 6 gigahertz processor, probably it's going to take a lot of power to be there. But actually, it turns out the best thing that you can do is actually pack more VMs to the same number of physical nodes, because the greenhouse gas emission, the embodied carbon for these servers is actually tremendously high. Mm-hmm. And also the static power and the background power of the server is actually quite high as well. So what you want to do is you want to provide, as a cloud provider, the same performance with less number of servers.
Got it.
Right? So how do you do that? You want to take calculated risks and have recourse mechanisms. Like overclocking is a good recourse mechanism. We can, as a platform, we can look at the performance and the importance of different VMs, mm-hmm. right? And go at the times that we need and provide more performance. We don't have cooling restrictions anymore, right. At least if you design the system properly. And it's the same story with designing services internally. So if you look at generic kind of service design, you basically have auto-scaling as a mechanism. This is very typical. You deploy an initial set of VMs, you do some provisioning, and you add a buffer on top. And that's your kind of resource for the number of resources that you have available for each individual service. Mm-hmm. Now, collectively, as a cloud provider, you want to minimize that. But how do you do that? If you deploy less resources and more load comes up, then what's going to end up happening is your tail latency will suffer. Mm-hmm. And you can get to the point where you will have maybe scale out, so you add more VMs, but this takes a lot of time because you need to replicate your state and everything. So this is also another important use case. And collectively, as a cloud provider, you can actually go and reduce the servers that you're using. Yeah. And that's probably the most sustainable thing that you can do.
Right. That makes sense, yes. That's excellent, yeah. So there's a lot of opportunity in this kind of, by doing cross-layer optimizations here. So this is awesome. Yeah. So Mark, how can the OCP community join this effort?
Yeah, first off, this is a pretty new technology, right? And there's a lot of different fluids out there, and people are bringing new fluids to market. And so, some of the things we saw earlier with the, how do we do BOM compatibility, that sort of testing. We saw the effect of contamination on performance. All those things need to be tested. For the servers, we just put air-cooled servers in there, but you can do a lot better because this fluid has a ton of capacity. So we could design new servers, much more dense. The pumps, the filters, all these things, every fluid needs a different filter, those sorts of things. Microsoft is, we're looking to contribute the server lifts. Service is a big deal. We don't want any, safety is utmost. And we're looking at doing more, bringing more of these operational learnings. We're considering a white paper, what would people want to see?
We're going to need to wrap up here, guys.
All right. You want to see us wrapping up. All right.
Sounds good. All right. So I'll say that we probably don't have time for a question.
We do not.
We don't. All right. So please feel free to talk to any of us offline. So thank you, everyone, for joining, and thanks to all our panelists.
Thank you.